It's 10, so we'll get started for the final time this semester. This is our last lecture. Um, Anything we cover here will be the only new information on the final exam that you have not been tested over. Um, so before we get into the actual material, just a couple things. One, so I have half the test graded. So if you don't see a grade for your test yet, that'll be done this afternoon. Then probably on Saturday, so I'll give people time to look at their grades. I'll update the um, the whatever test is dropped. And what I'm also thinking I'm going to do is I'll make because I get asked the question every single year, like, what do I need to make on my final to get such and such grade? So I'll probably just make an Excel spreadsheet available that I use to calculate that. So you can do that on your own. So I need to do that. Let's see. I will open up tests 1, 2, 3, and 4, make like copies of those tests so you can retake those as a way to test for the final exam to see if you still remember everything. And I'll put up a poll to see if people want to meet sometime next week, Monday, Tuesday, or Wednesday, to do some kind of final exam review over Zoom. Reminder that the final exam is open next week, Thursday and Friday. So you have all day Thursday or Friday to take it. And you'll have the take-home portion right here, as you can see on my screen. That will be due, I believe I said Monday, not this Monday, but the 10th at midnight, I believe I said that's due. All right, so one more thing. For today's lecture, I put up this file, molecular geometry sheet, and I'm going to try to have the PowerPoint in that sheet open at the same time, because what we're going to talk about today is how to determine the shapes of molecules. So I'm going to see if I can so the goal of today is to learn how to read that sheet and use that sheet. So I'm going to have the PowerPoint in that sheet open at the same time, but make sure, at some point you print out or have this sheet available to you when you take the final exam. All right, with that, I'm going to stop sharing the course content. And I'm going to share my whole screen for today because I'm trying to show two things at once. So keep in mind, if you if you send me a private message, it's not actually private because I'm sharing my whole screen. So just be aware of that. So right now, you should be able to see both my PowerPoint and my molecular geometry sheet on the left. So like I said, we're really going to learn how to use this sheet on the left to determine the molecular geometry of molecules, all right? And so the first concept we have to understand is this idea of electron groups. And what we mean by electron groups is how many things are bonded to the center atom. And this includes molecules or lone pairs, right? So in the example I have here, right, we have beryllium bound to 2 chlorines. So the number of electron groups connected to our center atom is 2. And when doing this, we really only care about the center atom for the most part. Same thing for carbon. We have 2. And here we have, it's called linear geometry. All right, how can we figure that out? That's this sheet on the left. So let's go over these columns. 1, total domains is the same as number of electron groups. They mean the same thing. So for our center atom, we have 2. So we go to the row that has 2 total domains. Then we have generic formulas, Ax2 or Axe, right? So the X is an atom. So X for that. So both of these molecules have a generic formula of Ax2, or the A is the center atom. Now let me talk about the E. E means lone pair. So if there's an atom, and it's written there, so I'm just recopying that image. So if an atom has a lone pair of electrons connected to itself, that is treated as one electron group. So our electron groups or domains are either something being bonded or a lone pair of electrons. But with the number of electron groups being 2 is relatively simple because it's always going to be linear. But let's continue looking at this sheet. So bonded atoms just tells you, okay, for your number of domains, how many atoms are bonded to your center atom. Ax2 has 2 bonded atoms. Axe has 1 bonded atom. How many lone pairs? Well, so Ax2 has no lone pairs. And remember, those 2 electrons, that's what we call a lone pair. While Axe has 1 lone pair. The shape, molecular shape and electron shape, right? Let's talk about these. The molecular shape is the shape of all bonded atoms. What I mean by that is when you look at the structure and you're just looking at the atoms that are present, like the atoms you can see, what shape does this molecule make? Well, the electron geometry is the shape of the bonded atoms plus lone pair. I'm just going to put LP for lone pair. So what I'm saying there is, for the electron geometry, you also have to look at the geometry of the lone pairs as well. And hopefully this will make a little more sense once we look at structures with lone pairs. So number of electron groups 2, that's easy. It's always going to be linear. Let's look at number of electron groups being 3. And we see this forms like a triangle with 3 atoms bonded. So this is Ax3. The shape is called trigonal planar. And since we don't have any lone pairs, the electron geometry is the same. So let's go to 4. Here is Ax4, tetrahedral. And for Ax4, let me actually draw a molecule that people will probably maybe be familiar with, and that's water. So this is water, right? So water also has 4 electron groups. It has 2 bonds to the hydrogen and 2 lone pairs. 1 lone pair, 2 lone pair. So for water, we would call this an Ax2E2. Remember, A center atom, X bonds, E electrons. While CH4 is just simply Ax4. Let's look at the molecular shape of CH4 versus water. And the molecular shape of Ax4, that would be tetrahedral. While for water, the molecular shape is bent because it is Ax2E2. We call that bent. The electron geometry for Ax4 is tetrahedral. While for water, it's also tetrahedral. So what that means is when you look at water in the 3D form, it looks a lot like this molecule. However, if you're just looking at the atoms, so imagine that you couldn't see those black scribbles. This is more or less what water looks like if you're just looking at atoms. So that's the bent geometry. While when we look at the lone pairs, then we can see the full tetrahedral shape. Right? So that's what we're going to be working on today. Just seeing if we can figure out electron geometries. Now, before I go on to the next slide, which has actual example problems, are there any questions about what I was talking about there? All right, so let's go to question 1, and I'm actually going to do B because B has lone pairs, right? So let's just see what are we doing. So for each molecular geometry, list the number of electron groups, how many of them are bonding, and how many of them are lone pairs, right? So here B, we have a more or less like kind of like a T bar going on, or a capital letter T. And I think it's tricky for new chemistry students to decide, when it's a lone pair there or not, because lone pairs are invisible. You can't see them, they're electrons. So the way I kind of decide the way to really know that a lone pair there is the atoms are kind of unnaturally close. What I mean by that is that atoms that are in bonds want to be equally spaced from each other, right? So imagine in B, if you just have 3 bonded atoms, naturally, they would want to be equally spaced from each other. They don't want to be near each other. However, if you look in B, they're not equally spaced, right? There's this huge gap at the top. And when you see big gaps like this, where you no longer have equal spacing, that's your cue, or that's your clue that lone pairs are there. You have invisible electrons that are pushing atoms unnaturally close to each other. All right, so that's going to be your hint. Now, once we realize that, the next thing to do is to look at this sheet. And what I do is I look at the pictures and figure out, okay, what image on my picture column corresponds to this atom. So I have at least 3 bonds, and I'm guessing I have at least 1 lone pair. So the number of electron bonding groups is 4+, right? 3 bonds and at least 1 lone pair. I don't know how many lone pairs there are just by looking at it because they're invisible. But let's start at total domain 4. And let's see if we can find a picture that looks like a T. So it's not Ax4. Axe doesn't look like a T. Ax2E2 doesn't look like a T. Axe3 doesn't look like a T. So for B, it's probably not 4 domains. Nothing looks like a T there. So let's go to 5 domains. That's not really a T. That's not a T. But this, Ax3E2, well, that looks just like B, right? Remember, the X's here are bonded atoms. These little globs are lone pairs, so they're invisible to us. You will not see those on an actual model. So they're just showing like where they would be if you could see them. So when looking at the geometry, just focus on the X's and the A's. So B looks like this T. So that's what we're looking at. So number of electron groups. Well, there would be 5 for B. Number of bonding groups. That's easy. There's 3. Number of lone pairs. 1, 2, 2. And even though I didn't ask this, just be aware that things I could ask are the molecular shape, which is called T-shape, and then the electron geometry is called trigonal bipyramid. Right. So any questions on how I figured that out? All right, so see if you can go through the other ones here and figure out, what type of molecular geometries we are looking at. If you have questions, let me know. But again, just as a reminder, any message you send will probably be seen by everyone else, even if it is just a private chat. But yeah, if you do have questions, let me know. Otherwise, let's see if we can figure out some geometries. I'm sorry, I did not know the chat was disabled. I just saw my emails. You should now be able to chat and ask your questions. So for letter B, what I wrote there was 5 electron groups, 3 bonding groups, 2 lone pairs. So EG, electron groups, BG, bonding groups, LP, lone pair. Then the thing above the arrow says 4 plus, because I was saying, I know there's at least 1 lone pair, so there's probably at least 4 bonding groups, if not more, or electron groups rather. on the chart, what are the dotted lines to X mean? So dotted lines, those of you who will take organic chemistry will probably learn about this, but those are telling you directions. So let me take Ax4 for an example. So Ax4 looks like this. The wedges are telling you that this molecule is coming out of the page towards you. The dashes are saying those atoms are going into the page or away from you, while these lines are saying it's in the plane of the page. This is a way to show a 3D structure. So we're trying by writing this to describe that geometry, right? Because these atoms are like coming towards us, these are going away. So this would be a wedge. This would be a wedge. This is a dash. This is a dash. And if it's in the same plane of the page, it's just a line. So since I just answered that, D is Ax4. So six electron groups, 6 bonding groups, 0 lone pairs. We'll do like a minute or two more of this. Then we'll move on to question 2. All right, so hopefully you got a little comfortable with that sheet. So let's go through this. And it's kind of hard to look at 3D models and figure out like what the bonds are showing. But for the most part, all these bonds are equal space. I mean, this one kind of does not look like it, but that's just the limitations of showing a 3D object on a 2D plane. So this only has bonding groups. So the electron groups here would be 4 electron groups. 4 of those are bonding groups and no lone pairs. For C, you can see there's like an obvious space missing here in the bottom where something should be, but we can't see it, which means that that space is taken up by a lone pair. So now our job is to find an image that looks like this, and that would be Ax5E. Remember, the dots there are showing you the lone pairs. So this would be Ax5E. So the number of electron groups are 6. We have 5 bonding groups and 1 lone pair. Already did E. or sorry, D. E, again, we have like something missing space at the top and bottom. For some reason, our atoms aren't going above or below here, which means electrons are probably there. They don't want to interact with those electrons. So there's probably a lone pair up here and probably a lone pair down there. And that would mean this would be Ax4 E2. Can you point to Ax5E? Ax5E is right here. So E is most likely Ax4E2, which kind of looks like this picture. So bonding group or electron groups, 6 as well. Whoops, 6 electron groups. 4 of those being from bonds, 2 of those being from lone pairs. So this is Ax4E2. Last one, F, is a little interesting looking. Again, there's empty space above or on to the left of F. No atoms are going there. So that tells us electrons are going to be there. So now we need to find a picture that kind of looks like this. And this picture that I'm hovering over kind of looks like that. This is called a seesaw because it kind of looks like a seesaw. So this would be an Ax4E, and Ax4E has 5 total electron groups. It has 4 bonding atoms, so 4 bonding groups, and 1 lone pair. So that is how we can use our sheet to the left here in these images to figure out, bonding groups, electron groups, and if we wanted to, molecular shape and the electron geometry. So before I move on to question 2, any questions about figuring this out? The sheet's hard to read, which is the generic formula under for all of them. So the sheet being hard to read, I think, yeah, you can, if you'd like, I have this as a word, and you can make it a little bit bigger, like that. And hopefully, when you have it printed out, if you want to do it that way, then it should be a little bit better to read, hopefully. You print it and it's still blurry. Okay. So let's see. That's not going to work. Well, I'll see if I can't find a better table. I mean, because these are just like generic tables that I found on the internet. So I guess I can see if I can find a better one. The subscripts like EX2 and all those. I mean, I wouldn't worry too much about that because all those subscripts are saying are just these numbers, right? AXE3, well, that's just saying 3 lone pairs, which are those. But yeah, so I guess I'll try and find another table. Let me see if I just do that. because we actually don't need that stuff. So I guess that's still a little blurry. Yeah, I'll see what I can do about that then. The E stands for lone pairs. Yes. Right. The X is just the number of bonds, right? The E is lone pairs. So honestly, like I don't ever use the generic formula. I just use the picture as best as I can as a way to figure out what I'm looking at. Right. So if there's no actual questions about figuring this out other than just being blurry, let's move on then. So let me make that big again. All right. So question 2. This time, I'm not giving you a picture. And we're going to use our Lewis structures to figure out the geometry. So here, let's do A, right? So we need to figure out what is the electron geometry, molecular geometry, and bond angles. We'll just say electron geometry and molecular geometry for these molecules. All right, so PF3. So we have to remember how to make our Lewis structures. So phosphorus has 5 valence electrons. Fluorine, oops, that's 7. Let me get my eraser. Did not want to put 2 electrons there. Fluorine, bond, bond, bond. Complete Lewis structure. So hopefully that's not a shock at this point for people. All right. So when doing this, all we care about is the center atom. So I'm not going to draw all the electrons around fluorine just to save some time. But this is PF3. And if we look, PF3 has 3 bonding groups, 1 lone pair, for a total of 4 electron groups. So I want to go down to 4 electron groups and see where there are, and let me scroll up a little bit. I'm trying to see, for 4 electron groups, what is the geometry of 3 bonded atoms and 1 lone pair? Well, the molecular shape, which I'm going to call MS, is trigonal planar. Oh, trigonal pyramid, sorry. While the electron geometry is called tetrahedral. Right? So it's the same exercise as in 1, but instead of a picture, I'm having you make the picture using your Lewis structures. So take a stab at this and see how you do. If you have questions, let me know. All right, so hopefully you're able to get like started on a couple of them. I know you probably did not finish them all. There are a lot here just for practice, but in the next couple of minutes, let's just do a few. So we're absolutely somewhat comfortable with this concept. All right, SBR2. So if you remember from your Lewis structures, halogens like bromine like to be at the termini, and usually multiple atoms mean you're at the termini as well. So sulfur has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Bromine has 7. So bond here, bond here. Everything has 8. Full octet, we're good. So sulfur, remember we only care about the middle atom here, has a total of 1, 2, 3, 4 electron groups. 2 of those are bonding groups. 2 of those are lone pairs. So if we go to 4 domains, 2 bonded atoms, 2 lone pairs, this would be the bent molecular shape. So molecular geometry is bent. And the electron geometry would be tetrahedral. So that's B. And I'm going to erase A here, get myself some more space. All right, so C, CHCl3. Usually, whenever you have carbon, carbon is generally in the center, and carbon has 4 lone pairs. Hydrogens, terminal. Halogens, also terminal. So hydrogen needs only 2 electrons, so 1 bond, we're good there. Each chlorine has 7 lone pairs, so halogens only want to make 1 bond. So now carbon has 8 electrons due to 4 bonds. Everything else has 8 electrons except hydrogen, which has 2. So we're all good. So in total, to our center atom, there are 4 electron groups. 4 of those are bonding groups. Therefore, we have no lone pairs. So if we go to our total domains, there's 4. 4 of those are bonding atoms. 0 are lone pairs. So both the molecular shape and the electron geometry are the same here. They're both tetrahedral. So that's C. Any questions on B or C? How did I find there's 2 lone pairs for B? Well, remember sulfur is right below oxygen. So sulfur has 6 valence electrons, right? Bromine has 7. So when we do our octet rules, bromine is a halogen and only wants 1 bond. So making 1 bond gives it 8 electrons. The other bromine only wants 1 bond, so that'll be 8 electrons. Now sulfur has 2, 4, 6, 8 electrons as well. Each one of these pairs of dots is a lone pair, right? So when making a Lewis structure, when you make it, you'll have 2 lone pairs left over. And that's how I figure out there's 2 lone pairs, just by making a Lewis structure. That makes sense? Yeah, 2 dots, 1 lone pair. All right, D, CS2. So remember, carbon is usually going to be in the center. Carbon has 4 valence electrons. Sulfur has 6 valence electrons. So remember, the goal is to get to 8 electrons. So sulfur has 6, carbon has 4, sulfur has 6. So we make 1 bond here. Carbon has 5, sulfur has 7. We make another bond here between the carbon and sulfur. Carbon now has 6, sulfur has 8. This sulfur is good. So we make a bond from this sulfur to this carbon. Carbon would have 7, sulfur has 7. Make another bond from the sulfur to carbon. Sulfur has 8, carbon has 8. I'm going to redraw this to make it neater. Oops, start a little farther away. So carbon disulfide has carbon in the center with a sulfur on each side being double bonded. Now, just because it's a double bond does not mean anything special. Treat a double bond, a triple bond, and a single bond the same when it comes to bonded atoms. So in total, this carbon only has 2 electron groups, right? It has 2 atoms bonded to it. I don't care if it's a double bond or a triple bond. All I care about is the number of atoms bonded. So in total, 2 atoms are bonded. So we have 2 bonding groups and 0 lone pairs. So this would be the linear geometry. Because I'm total domains of 2 bonds, no lone pairs, so linear, linear. For both the molecular and electron geometry. Questions about D or any of the other ones so far? All right, so I'm going to skip E because we have time for exactly 1 more. So let me do F because F's more complicated than E. So F, we have nitrogen, 5 lone pairs. Or sorry, 5 valence electrons, not 5 lone pairs. Fluorine, 7, and we have 3 fluorines. So 3 bonds, right? Because originally nitrogen has 5, and to get to 8, you just make 3 bonds. Fluorine had 7, so to get to 8, you just make 1 bond. So this is, draw it a little bit neater there. Looks like this. Excuse me. So we have 4 electron groups, right? Lone pair, 3 bonds. So 4 electron groups. 3 of those are bonding groups. 1 is a lone pair. So we're going for 4, 3, 1 again. 3 bonded, 1 lone pair. So this is trigonal pyramid. That's our molecular shape. And the electron shape is tetrahedral. Right. So last call, questions about what we're doing here in terms of Lewis structures and molecular geometries. And I believe question 3. Yeah, question 3 is the same idea as question 2. It's just more practice. Can we do E? Sure. E is super easy though. It's the same as C. I can do that really quick. And in fact, all I'm going to do is here's C skeleton, and I'm just going to use that. Right? Because carbon has 4 valence electrons. Fluorine has 7 valence electrons. One, 2, 3, 4. So it's the same answer as C. Basically, all you're doing is instead of having hydrogen and 3 chlorines, you just put 4 fluorines instead. So anything, if there's 4 things bound to carbon, it's always the same answer. Tetrahedral. And that is like one of the most common types in all of chemistry. All right, so even though we didn't go over question 3, make sure that you practice it because it's just more examples. But yeah, we're not going to worry about polarity. Polarity, we will just skip that because we didn't have time to go over that. And that is a new concept. Yeah, determining polarity won't be on the exam because we did not cover it. Other than that, so this is the last time that we have class. Like I said, I will send out like a poll sometime in the near future about times when people might want to come together, and I'll let you know the results of that. Otherwise, yeah, I'm glad you enjoyed it. Hopefully you learned some stuff. Hopefully you see the world a little bit differently now that you understand that it's made out of these tiny little magnets that hold everything together. But yeah, study hard. Good luck on your final. Don't stress too much, but study hard. If you need anything from me, let me know. Otherwise, have a good weekend, good week. Take care.